pleasure as well as honor to introduce Mitch Philpot, who everybody here knows and loves. He's been a UU since 1964 when his family moved to Houston. We're not going to say from where, he can if he wants to, and a member of this fellowship for many, many years. He had a large chemistry set as a child and became a lifelong science nerd, as he proudly calls himself. Went on to become a science teacher, from which he is now retired. He also enjoys music, cooking, fishing, genealogy, reading, birding. I'm not sure when he had any time for anything, but anyway. And working with the Texas Master Naturalist and the Nature Conservancy of the Texas City Prairie Preserve, where he works with others to help preserve the endangered Atwater's prairie chickens. Our local science teacher is coming out of retirement today, helping us look at our universe from our local galactic group down to tiny subatomic particles. Joining him, a science teacher, will be mad scientist Mitch Philpot, who will have several physics experiments for us. He'll start with a story for all ages, and we would be having singing of the children on the way, but I see that they're already gone. So in our hearts anyway, we sing the children on the way. Mitch, mad scientist.
One of my favorite authors here. This is James Thurber, and this is Fables for Our Time. I highly recommend it. The Moth and the Star. A young and impressionable moth once set his heart on a certain star. He told his mother about this, and she counseled him to set his heart on a bridge lamp instead. Stars aren't the thing to hang around, she said. Lamps are the things you hang around. You get somewhere that way, said the moth father. You don't get anywhere chasing stars. But the moth would not heed the words of either parent. Every evening at dusk, when the star came out, he would start flying towards it, and every morning at dawn, he would crawl back home, worn out with his vain endeavor. One day his father said to him, "You haven't burned a wing in months, boy. Look at you. You're never going to do anything like this. All your brothers have been badly burned flying around street lamps, and all your sisters have been terribly singed flying around house lamps. Come on now, get out there and get yourself scorched. A big strapping moth like you without a mark on him?" The moth left his father's house but would not fly around street lamps. He would not fly around house lamps. He went right on trying to reach his star, which was 4 1/3 light years away, or 25 trillion miles. The moth thought it was just caught on top branches of an elm tree. He never did reach his star, but went right on trying, night after night. And when he was very, very old moth, he'd begun to think that he had actually reached his star, and went around saying so. This gave him a deep and lasting pleasure. He lived to a great old age. His parents and brothers and sisters all been burned to death when they were quite young. Moral: who flies afar from the sphere of our sorrows is here today and here tomorrow. Yeah. Okay. Welcome to our universe. Can you start the slideshow? So we're going to be, I'll go ahead and start. We're going to be talking about the universe, the big, the tiny, and everything in between, okay? And I'm going to be using a couple of hand signals, okay? One is this. This is a head scratcher. We'll have several of those. And the other one is this. This is a brain twister. This means you're going to have to bend your brain into a little bit different shape for some of these ideas to fit in. And I even brought along some cerebral Bengay for brain strain, because we're going to need it. So, my first encounter with the universe was when we were little kids. We would go and sit on the blanket in front of the television and look at the Indian test pattern and wait for the Flash Gordon serials to come on. This was 1936, Buster Crabbe, and of course it's Flash Gordon conquers the universe. Okay. No little bits for him, okay? And then my second encounter with the universe, which I love, it's the most pretentious of all, is the Miss Universe pageant. Yeah. Let me tell you, when I see some Star Wars looking creature go down the runway on tentacles with eye stalks and a tail, then I'll believe, it's the Miss Universe pageant. Here's Miss Alpha Debrin, So, no, okay, I don't think so. So, the first thing is, how old is the universe? So we'll look at that one first. And here's what you kind of have to imagine. First, they looked out at the universe and they noticed, and you may have heard of this, that everything is moving away from us. Okay, and the further away it is, the faster it's moving away from us. Okay, so the only way they could explain that was by saying, well, the actual space in between everything is actually expanding, and that's what they came up with. Okay. Then to figure out the age of the Earth, the universe, what they did was they said, okay, imagine I got a firecracker and a really high-speed camera taking a picture of it exploding. And I don't get the first part of it, but I see this part of it exploding, okay, and I can watch the video. Well, I can mentally run that video backwards, right, to get back to the original firecracker and figure out how long that takes. And that's pretty much what they did, okay? 13.8 billion years, okay? And this is a demonstration of what they're talking about. This is commonly demonstrated of the universe expanding. Little dots on here, and what happens is they get further and further apart. Okay, but the ones farther from this one get further apart faster because it's actually the space in between the dots that's expanding. So now I want to take this off. This is our universe here. And this, by the way, is simply a little valve, okay? It's closed now. This is open. So things will go through it, okay? Little device that I made. And we're going to attach our universe going into that, okay? Now, we're going to get another universe. And this is going to be your first test. I have several of these of how the universe works, okay? So, I'll put our big universe. It's going down. It's leaking. Okay. All right. Sheet. Okay. Okay. So now, let's see if I can get this one here better. Okay. Put this, our smaller universe, on this end. There we go. Okay. So, there we go. So it's pretty obvious now what's going to happen, right, when I connect the two universes. I mean, we're no fools. Okay, we know how the universe works, right? Or maybe not. Here's a head scratcher, okay? I'll set this universe over here for a little bit, all right? So, and here's another funny kind of thing that one of the strange things that happens in little ironies of science is that they came up with this theory of the Big Bang, but how do you prove something like that? It was really hard for them to come up with something. And so it was just a theory until finally these scientists figured out, hey, you know what? If this thing happened like that, there would be like an echo out there, a little microwave echo of the Big Bang. And so they started looking for it. Well, the problem is they didn't have a microwave antenna big enough and strong enough to pick it up. We knew it was going to be really weak. They said, I know who does. The Bell Laboratories. Because this is back when they were investigating using microwaves for telephones. So they had a huge microwave antenna. So the astronomers go over there and they say, hey, we want to try to find this on your antenna. And the guy said, yeah, well, we're still working on it. We're having this one problem with this antenna. No matter how much we clean it and where we point it in the sky, we always get this strange little microwave background noise. And the astronomers were like, what? So the stuff they were trying to get rid of was the stuff that the astronomers were looking for. And they found it, and they actually won a Nobel Prize because this was the first evidence, actual evidence of the Big Bang Theory. Okay. Now, we're talking about the age of the universe. Let's look at the age of the Earth. Let's see. Next slide. Okay. Now, this is kind of in between. This is what the scientists have been trying to do since about 1500. Okay. Trying to figure out what the universe is and how it works. You see the guy peering around the corner, behind the curtain. Who's that behind the curtain of the universe? And this was like from 1500s, and we've been trying to do it ever since. We've just been getting a little bit better at it. Okay. Now, a little break here. The age of the Earth. Okay. How old is the Earth? Yes, next time. Okay, this is a model. There's a couple of models of how old the Earth is here. This one uses a clock, and it says, this was happening if the whole age of the Earth was boiled down to 24 hours. What was happening at this hour? What was happening then? And of course, what it boils down to is the entire history of all people on Earth is like the last 2 seconds of the last hour, of the Earth. And the next one, so that's kind of one way to try and view it. And here's the most, nope, you missed one. Nope, oh, here. That's the next one in line. Okay. See if this is the next one. Nope, okay, never mind. Well, there was another slide that's supposed to be in there. I don't know what happened to it. Nope. Okay, back to that one. But what I tried to do with my students is I said, well, let's just make a real timeline of the planet Earth. Well, the problem is the planet Earth is 4.5 billion years old. Okay? So what do you do to make a 4.5 billion year timeline? Well, the first thing I figured out was you're going to need a really long piece of paper. And what we did was we pulled out a piece of paper that was 4.5 meters long. So there are 1,000 millimeters to a meter. And if you want to make that into a timeline, that means every millimeter, that's about the thickness of a dime, is 1 million years. Okay, and here it is. Okay, so there is 4.5 million years ago. Now, 500,000 years later, there is the first life on Earth. And that happened to be a blue-green algae bacteria kind of thing that actually had photosynthesis and produced oxygen. Now, the problem is, bacteria don't like oxygen, and so they try to get rid of it. So this thing was pumping out oxygen all the time, and all the time is a long time. From here to here, okay, that's 1.5 billion years, okay, of nothing but slime in the ice machine, basically. Okay, but it was putting off oxygen. Actual life as we know it starts here. All of that, little bacteria, one-cell animals, and then in the last, that's when everything happens. Everything else was slime in the ice machine and amoebas. Okay? And the good news is that for all this time, those little things have been pumping out oxygen, and somewhere in here, there finally got to be enough oxygen on Earth for other living things to survive. And there's actually a funny thing in geology called the black-red shift, where all the iron, and there's lots of iron on Earth, was black, all of it, for the longest time, because there was no oxygen to rust it. And then all of a sudden, if you look at these geologic layers, there's all of a sudden all these red layers now because there's enough oxygen in the atmosphere to rust iron. Okay. So we get down here to the last 5 million years, okay, and that's this big. So we did like they do on maps. You know how they have like a little inset that's blown up on a map? So we blew up the last 5 million years to 500 millimeters, and that's it there. And still, okay, the history of all of mankind is about this big. On the regular size thing, you're talking about like the thickness of a piece of cigarette paper. Do we feel humble yet? Okay. I look at this and I think of some people like Putin, you know, out there with all their saber rattling and flag waving, and I'm like, you know, this is like an ant telling a flea how big he is. Okay. Now I got another model here that I'm going to show you, and this is more down to earth here, a model of our ecosystem. Okay. Now you've used this many times when teaching conservation and ecology, and we have things that make up our ecosystem: clean water, rain. Okay. People, for the better or the worse, they're here. Okay. This guy, who I was working to save, this is the Atwater's prairie chicken, very endangered. And of course, everybody needs food, something to eat. Okay. Now, in this model, okay, what we know is that there's 4 objects and 2 strings connecting them together. Okay. So we're going to do scientists here and come up with some ideas. Okay. But we don't know exactly how these are put together, but we can come up with guesses. What do you call a scientific guess? Hypothesis. Why? Because what's our best guess so far doesn't sound near as good as this is our latest hypothesis. So what would be the simplest way? What would be the simplest hypothesis of how these are connected? Right? Maybe just like this, right? A to B, C to D. Now, I wanted to get tricky, right? I could cross them up. Or if I wanted to get really nasty, I could make this one little short string here and this one long string. Okay? So there's 3 different hypotheses. So what does scientists do next? Experiment, test our hypothesis. Simple enough. Okay? So we pull on one of these objects and see what moves. Okay? So pull on this one and look, it moves. Okay? And I pull on this one. So which hypothesis is correct? A. Okay, our first hypothesis. Okay, it can't be this, right? Because if it was that one, and I pulled on this one, that over there would move. And if I pulled on this one, that over there would move. Okay. Well, what happened here? At least we know it's not this one, because if it's that one and I pulled on this one, that one would move, and then that one would move. You keep these balloons company over here, okay? Set this aside for a second. Okay. Now, one of the other things I'd like to point out, on this little timeline here, way down there at the end, plants got invented and coal beds were formed. Okay? So how many people in here have a diamond? Okay? So I'll tell you a story. All right. The coal forms, okay, and then it gets buried. It gets buried deeper and deeper, and under all this heat and pressure, okay, the coal turns into diamonds, right? Have you heard that story before? Only problem is it's total BS. There's not a word of truth in it. Okay? One of the reasons they found out how old the Earth is they radioactively took the ages of rocks, okay, and they kind of like carbon-14, but with different minerals and way deeper ages, okay. Now, when they did that to diamonds, they found that all diamonds were 1 billion to 3 billion years old. Way back here, no plants at all. So where did those diamonds come from? Well, it turns out that volcanoes are notorious for spewing out carbon dioxide. There's lots of carbon in a volcano. And what happened was a tube would form from way down in the middle of the earth up and break into a volcano at the top. Well, about 100 miles down that tube, there's enough heat and pressure for that carbon in the carbon dioxide to actually crystallize into diamonds. And that's where the diamonds come from, not from coal, ever. Okay, so diamonds form in volcanoes. And then billions of years later, that is pushed up to the surface of the earth and becomes what is known as kimberlite. And that's a geologic formation where diamonds are found. Now, I also have some really wonders of the earth up here, and I'm going to stay here for a while after the service and let you come up, and please come up, touch them, pick them up, look at them. Okay. Now, next question: how big is the universe? Okay. Really, really big. Remember Carl Sagan, billions and billions? Well, if you're going to talk about how big the universe is, it's worse than billions and billions, okay? And it's really hard to kind of get a grip on this big of a number, so I'm going to try and do a little exercise to help us out, okay? When you were 1 million seconds old, how old were you? Look back after 1 million seconds, you were 11 and a half days old. You had not even used up your first bag of diapers, okay? But now, when you're 1 billion years old, how old are you? Okay? Our next step up. After 1 billion seconds, not days, not weeks, seconds, 1 billion seconds, you're 31 years old. Now, get ready here. Okay. If that's a billion seconds, a trillion, right, is 1,000 billion. So 1 trillion seconds is 31,000 years. That's when we were figuring out how to make stone tools. Okay, so that kind of, maybe we can get a little bit of a mental grasp on how big those numbers really are. Okay. Now, and here is, since we're talking about our universe, here's a neighborhood map of our universal neighborhood. Now, we judge things on the size of the universe by light years, okay? And what that is the amount of distance light travels in 1 year. Okay, light travels at 300,000 meters per second, okay? And so there are, 3 million seconds in a year. So that's 300,000 times 31 million. That's big, okay? And just to give you some other kind of grasp on this, it takes 1 1/3 seconds for light to get from here to the moon. Okay, it takes 8 minutes for light to get from the sun to us. And here's one of the problems they ran into. Okay? For light or any kind of thing that travels at the speed of light to get to Mars, it takes 12 minutes and 42 seconds. Now, this turned into a big problem when they sent the Mars rover up, because here's this guy with his joystick trying to control the Mars rover. Yep. And he goes, oh, go forward. Uh-oh, I'm about to run into a rock. Well, first you have to realize that he was about to run into a rock 12 minutes ago. And so what he's seeing was what happened 12 minutes ago on Mars. Okay, so then he says, stop. Well, it takes 12 minutes for that signal to get to the Mars rover. Consequently, that Mars rover went very, very slow. Okay, little problems with light speed. Okay, so 1 light year then winds up being about 6 trillion miles. 1 light year. Okay, and here's our local neighborhood. Okay. Now, what it shows is here's our solar system, right, which doesn't even rate, not even a fraction of a light year across. Now, here is what they call our local group. Okay, local group is 2 million light years across. For universe, that's local. Okay, that's 2 times 6 trillion miles. Okay, it's huge. Okay, and so then you get, oh, and that, by the way, includes the Andromeda Galaxy. Okay, and I'm going to head in here. The Andromeda, now don't everybody jump up and run to the door at once, okay? But the Andromeda Galaxy is moving straight towards the Milky Way galaxy, okay, at a rate of 200,000 kilometers per hour. That's faster than a speeding bullet. Now, why not to worry? Because at that distance it would take 2 billion years to get here. Okay. And so here's the larger group, 200 million, because here is the edge of the universe, which they list as 200 billion, no, 20 billion light years to the edge of the universe. Now, trying to figure out the edge of the universe is kind of a thing in itself, okay? The expansion rate of the universe is 73 kilometers per second, okay, for every 3.2 million light years. Okay, so that means that at 3.2 million light years, something's going to look like it's moving away from us at 100,000 miles an hour. Okay. So it's big. The current one, okay, the current size of the universe since the Hubble Telescope, by the way. Yeah, next slide. There's some problems trying to figure out the edge of the universe because one way is to say, okay, if everything's moving away from us that fast, at some point things are going to be moving away from us at the speed of light. So here's how you have to think of that. If a car is passing you at 60 miles an hour, and a guy sticks a cannon out the window and shoots a cannonball at you at 60 miles an hour, that cannonball is going to look like it's standing still. Now remember, the guy in the car is moving away from him at 60 miles an hour. It looks fine to him, but to you it's going to be standing still and just drop to the ground. So at some point out there, light trying to reach us, we're moving away as fast as the light's trying to get to us. And so the edge of the universe is kind of like an event horizon in that sense. But there's problems with that. So next slide. So what they did was say, let's try this. Let's pick the furthest thing away that we can see, okay, and see how far away that is. They found this thing. It's a spiral galaxy, and you can tell by the kind of the color of it, it's way red shifted. It's way moving away from us. They did some calculations. It is 13.4 billion light years away, okay? Except for one thing. The light from that galaxy It's taken 13.4 billion years to get here, right? But for all of that 13 billion years, all the space has been expanding. And so when you add that to the calculation, you get 32 billion light years. Okay, 32 billion times 6 trillion. Okay, and most astronomers have just said that's the edge of the universe. Okay. Now I'm trying to hurry this up a little bit. Next thing is, how does the universe work? Okay. And well, let's go ahead. Go to the next slide. I'm going to do just a little real quick of who's been looking at the universe. This guy is Copernicus, right? One of the first ones to figure out that the Earth was not the center of the universe. Very smart man, yes, and he was really smart. He gave the book to his publisher on the day that he died. Okay. So it was published 8 years after his death. Okay. Next slide. Because they were having quite a time. This is the next one that came along, Galileo. Okay. And a little background of how he got into so much trouble. Okay. Back in 1517, Martin Luther nailed his thesis onto the door and started the Protestant Revolution. Okay. In 1500, okay, William Tyndale was burned at the stake for printing the Bible in English. That happened quite a lot during King Henry VIII's reign. You know, he took the church over, and people were reading the Bible in English, and people were burned at the stake for reading the Bible in English. Okay, and then, okay, a guy named Giordano Bruno was an astronomer. He's right in the middle of when Galileo was doing this stuff. They hung him upside down and burned him at the stake. Yeah. The other guy they had a little mercy on. They strangled him first and then burned him at the stake. Now, one of the funny things is back then, the saints and everybody, they had relics. You know, a finger of a saint or a hair lock from a saint, a piece of the cross. When they did the inventory, there was enough pieces of the cross to build a cathedral with. Yeah. But somebody, before Galileo was buried, decided to take a relic from Galileo, and they cut 3 of his fingers off, okay, and preserved them in little glass cases. Okay. One of them wound up in a museum, Florence, okay, in a little glass case, and according to the legend, it's pointed at the local cathedral. Guess which finger it is? That's Galileo's parting shot at the church that gave him so much trouble. Okay. Yeah. Next slide. These are some other people that were really instrumental. This is Edwin Hubble, the guy that the Hubble Telescope was named after. And he was the one that first figured out redshift. And this is back in the 1920s. He was just getting really good telescopes and learning how to shoot photographs with open lenses for a long time. And he was the one that figured out that every little fuzzy cloud out there that people thought was just a little bit away was actually the Andromeda Galaxy. And when he did that, it was almost like back when they said the Earth was not the center of the universe. They said, we're not the only galaxy. There's all, and then, okay, next slide. Okay, here's another really famous one. I love Stephen Hawking. Okay, and then that's next. Oh, okay. Well, one thing. He got a little bit mixed up, but this was the thing that threw everybody way off when they were first set up the Hubble Telescope. And here's another funny story. The guy that was directing the Hubble Telescope said, well, I'm going to take this thing, I'm the director, I get to say this, and point it at the sky for several days and just leave the lens open. This is what they got. And this totally blew everybody away. Okay? They were not expecting this at all. They thought just little fuzzy gas clouds, maybe a few stars. Okay. Everybody had to throw what they thought about the universe straight out the window. Okay. And it was a monumental moment in astronomy. Next. Oh. What the universe is made out of, okay? And how does it work? Well, you recognize this. This is the periodic table of the elements. And I have some old textbooks that say, well, there's only going to be 92 elements. That's it. Uranium is the last element. If you try to make any more elements, they're just going to fall apart. And of course, you can see we've got at least a dozen after uranium, and you probably have one in your home. Okay? If you have a smoke detector, look on the back of it, it says contains americinium, a man-made radioactive element, number 95, okay? And that's what makes smoke detectors work. So that's basically, now here's the other funny thing. 99.9% of the universe is made from the first two elements on the list, hydrogen and helium. Why? Because that's what's in the stars. All the rest of the stuff is only a tiny fraction of it. And next slide. And this is the ingredients list of the universe here. This is what all the elements are made out of. Okay, protons, neutrons, electrons, and then there's strange looking stuff. Look at the top up there. There's photons and neutrinos. And the mass is listed as 0. A particle with 0 mass. Okay. And when I'm looking at this, I start thinking, you know what? How do you really get a grip on? How do you train your brain to think about these things? Maybe we should listen to the sound of one hand clapping. Okay. I'm starting to think that the spiritual world and the physical world are not that far apart. You know, people used to think that light and matter were just two separate universes until Einstein told them different. Okay. Now, I don't want to push this too long. I'm going to wrap up here. So I'm going to show one more how the universe works demonstration. Okay. We're talking about force here. Okay. So that is a rat trap, not a mouse trap. That's a rat trap. A big double spring, big rat trap. Okay. So I've got two of them here. Get this thing to be still. Okay. This one is tied back with this spring is tied back with a string. It's not set. Okay. The mechanism's been taken off. There we go. Okay. This one's a regular mouse. We're talking about force. Yep. Lots of force. Okay. Now this one, tied back. I'm going to light the string. Next test of how the universe works. So what's going to happen? Wham! This thing is going to go flying like a helicopter. If I can get this thing to work. What happened? What happened? Why didn't I get slapped by a rat trap? Okay, so let me just take a break here. We're going to this thing up and explain the universe. Okay. First off, let's look at this thing. Okay. It's supposed to equalize it out, right? Well, it did equalize it. But volume is not a force. The force involved here is pressure. When you're blowing up a balloon, when do you have to blow the hardest? Right when you start blowing up the balloon. So this one had more pressure in it. So this thing here. This is the Penn and Teller version of my Echo 2. Now, you see, it's got the 4 objects, it's got the 2 strings, but they're crossed. So, if I pin this loop down here and pull on this, it just slides around inside. See that? And if I pin this here and pull on this, the same thing happens here. But if I pin this one down and pull it, look what happens. See, that loop gets longer and shorter, and the same thing here. So that those two move. And if I don't hold anything at all, it just does that. So that's how that thing works. Now, how did this thing work? Why didn't this thing go off like a helicopter? Well, when I pull back on this ring, okay, look at this. See the pressure on my hand? It wants to take this piece of board, sling it that way, really far. Now, when it hits on this side, it hits going the opposite way. With how much force? That same force. Okay. So it hits with the exact same force, okay, on the other side, and it doesn't go anywhere. So it didn't hit me. I was protected by the law. For every action, there's an equal and opposite reaction. Newton's second law of motion. Now, doesn't that sound something like a spiritual law we know? The law of karma. Yeah. So, I'm telling you, the spiritual world and the physical world are just not that far apart. They're all one universe. So, and other thing you find when you look at this is that there's all signs of uncertainty and randomness, okay, and chance in the universe, and it's built into the universe. Okay, it is part of the fabric of the universe, and that doesn't disappoint me that I can't explain the universe. It makes me excited because that means that the universe is always going to have a degree of mystery in it, and that's the kind of universe I like. So thank you for your time. Namaste.